Welcome to my fourth experiment video for the Physics 1010 class. Today we will be investigating the connection between entropy and probability. Entropy is a measure of how much thermal/internal energy is dispersed. In more colloquial terms, it's a measure of the amount of disorder or chaos in a system. Meanwhile, probability is a measure of the likelihood of a random event occurring. We will investigate the relationship through the model of coin flipping. First, we will look at three graphs that count the number of possible ways that 4, 20, and 100 coins can land heads up. As we can see from them, for 4 coins, the outcomes with the highest number of possibilities are for the ones between 1 to 3 coins landing heads up. This changes to 5 to 15 coins landing heads up for 20 coins, and 35 to 65 coins landing heads up for 100 coins. Using the given data, what is the connection between probability and entropy? Well, the connection is that generally, for a given system, a high entropy state is more likely to occur than a low entropy state, due to the second law of thermodynamics. In context, it means that on a given roll, we're more likely to get an event with a high number of possible outcomes than an event with a low number of possible outcomes. Does the likelihood of seeing a high entropy state versus a low entropy state change if you increase the size of the system? Well, yes, it does. As an example, the probability of getting 2 heads changes from 0.3750 to about 1.812 times 10 to the minus 4 as we increase the number of pennies from 4 to 20. Likewise, the probability of getting 10 heads changes from 0. to about 0.1762 to around 1.365 times 10 to the minus 7 as we increase the number of pennies from 20 to 100. Seeing how the most likely event becomes unlikely as we increase the size of the system shows how the bigger the system, the more likely we are to obtain a high entropy state. Third question is, would you accept a deal that would give you an A in the class if you repeatedly tossed 20 pennies and managed to get 0 heads on a toss by the end of the semester, and an E if you didn't? Well, the probability of getting 0 heads when flipping 20 coins at the same time is equal to 1 over 2 to the power of 20, or about 9.537 times 10 to the minus 7. As such, the average number of attempts we'd need to do to get no heads when flipping 20 coins simultaneously, which is found by taking the inverse of this probability, is 1,048,576. If we were to assume a generous rate of 20 coins being flipped per second, the average time required to get no heads when flipping 20 coins simultaneously is 1,048,576 seconds, or about 12 days and 3 hours. Due to the low odds and the length of time required to obtain this outcome, it's reasonable to reject the deal as it is not worth to go through it. So far, we've only looked at this model based on what happens by chance. Is it possible to make any of the systems go to 0 heads? Yes, it is possible to forcibly make all the coins from the previous system land on tails and not heads. All we'd have to do is simply flip all the coins that landed on head so that the tail side of the coin faces upwards. While self-evident, it illustrates an important concept to keep in mind when talking about the second law of thermodynamics in the context of molecules, that it only applies to an isolated system where no work can be done by the environment on the system, as our solution involves us doing the work on the system of coins. Before we answer question 5, we need to collect some data, so we're going to go ahead and do that now. This is the setup that we're going to use to answer the 5th question. We have a tray, we have a cup, and we have a total of 20 pennies. We're going to take 4 out of these 20 pennies. We're going to shake them inside of our cup. And then we're going to toss them on the tray over here. and we're gonna count how many pennies landed on heads out of the 4 pennies. So in this instance, it would be 2 pennies landed on heads. So we're gonna put in 2 for this run. We're gonna do this until we have 0 heads and we get 2 heads, which in this case has already happened. For the second part of this experiment, we're going to be putting all 20 coins in a cup and repeat the same process we did before. We're going to shake them into the cup, and then we're going to let them out on the table, and we're going to count the number of heads that landed. So in this case, it would be 7, 8, 9, 10, 11, 12, 13, 14. So we put that into our table. And we're going to continue this until we have 50, we've done 50 throws. Now that we've collected our values, let's do some analysis. We'll first start with the 4 coins trial, where we were able to go as high as 24 runs before we finally rolled 0 heads. This is the table of all the runs. And this is the table of the frequency, expected frequency, proportion, and expected proportion for each given number of heads. From this, we have plotted 2 column graphs for this experiment. First of the measured versus expected frequency of 4 coins landing a given number of heads, and then the same for proportion. As we can see, while not exact, the distribution of our measured values closely matches the distribution of the expected values, where most of our data are within 1 to 3 heads, and the outcome with the highest frequency / proportion also being that of rolling 2 heads. Next, we'll look at the 4 coins trial, where we did a total of 50 runs. Similarly, this is the table of all the runs. This is the table of the frequency, expected frequency, proportion, and expected proportion for each given number of heads. We have plotted 2 column graphs for this experiment. First of the measured versus expected frequency of 20 coins landing a given number of heads, and then the same for proportion. In the same way as before, most of our data lies within 5 to 15 heads, and the outcome with the highest frequency / proportion is also that of rolling 10 heads. With this, we can answer the 5th question. Do your results in the 2 experiments support your analysis of the given data? To that, I would say that the answer is yes, since the empirical data closely resembles the given data. Thanks for coming to my video, and I hope you have a good rest of your day.